Okay, can you hear me? Can you hear me there?
Yes, sir.
Okay, now, as I told the other students, basically we're going to be going to the other slides. The other slides are pretty good for this section. In one respect, it's kind of nice to see that there are some good slides that the other slide set don't fit it. So basically, we're going to be using those today. So I'll be switching to those. Basically, some announcements. I said this to the other students here. We will have another worksheet for you to work on over the weekend. I will, and basically email it to everybody. So just work on that worksheet over the weekend. If you have questions, email me about it. And just make sure you know how to do everything by Monday. That'll be on this chapter. And then lastly, there'll be another worksheet that I'll hand out, that I'll email to everybody on Tuesday next week that you can work to prepare for the 4th test. And basically that's just practice 2. And so I encourage you to make an effort to do well on that and ask me if you have any questions there too. But basically also please, so I can get a count, how many of you who are virtual have a class at 10 a.m. on Thursday next week? We have our class at 9, class at 10 a.m. How many of you have a class at 10 a.m.?
I do.
I do.
I have work.
Huh?
I do.
4?
I do.
I do.
Okay, 5, 6. Any more? Just 6? Okay, it sounded like.
I do.
Did you hear me, Dr. Douglas? I did too.
All right, let's do it again. Let's do it again. In order, pick number 1. So Paige, you're number 1.
Yes, I have a 10.
Next person.
I have a 10.
Say 2. Say 2 for the next person.
2.
Okay.
3.
Okay.
4.
4 and 5. Okay. Okay.
6.
6. Any others? Okay, looks like 6. So you folks come at 9 o'clock on Thursday next week for your exam. Okay. And do we have 6 volunteers who could come at 10? So we have the things. Can you come at 10? Anyone else can come at 10? Okay, so basically 6 of the people here will come at 10. So basically we'll get everybody in either at 9 or 10 o'clock. But those of you who have a 10 o'clock class, a week from Thursday, a week from tomorrow, come at 9 o'clock for your 4th test. Okay, and then you'll get 55 minutes. And then the other group will be at 10 o'clock. Any questions regarding how that's going to work? Okay, someone put a chat. I'll see what they wanted to ask me. Okay.
No, I was just saying I do.
Okay, that was from you, Nick. Okay, that's fine. Okay, so basically that covers that. Okay, now are there any other questions anybody has regarding how this is going to work? Now, today I'm going to go to the other slides for our textbook because they are very good for the portion that I'm going to cover today, and then I will finish chapter 8 tomorrow. Then on Monday we will do chapter 10, which I believe is the gas laws, and I'm going to be covering the basic gas laws and the ideal gas law, and that'll finish it off. So you get a good overview for that. But basically that's just math and learning how to use the equations. And you can even start practicing that stuff over the weekend if you wish to study it earlier. Okay, so now are there any questions regarding what's going to happen for the next week and a half?
So we have a test next Thursday?
Yes, and basically the people that have classes at 10 o'clock next Thursday basically will come at 9, and then the others will come at 10 to finish off.
When is our final?
The final, I believe, is a week from Tuesday. Tuesday, right before Thanksgiving, 8 o'clock in the morning, and you get 3 hours. But I don't know how long the final exam, the department exam will be given. So basically we'll split the people in that 3 hours time. So it might be an hour and a half for the exam, and then the first group would come at 8, the second group would come at 9:30 or something like that. That's yet to be determined. But it's the official schedule that's on the thing, and we haven't made modifications to that yet. It's the official schedule for Monday, Wednesday at 10 o'clock, and then Thursday at 8, Thursday at 9. That meets at 8 o'clock on Tuesday, right before Thanksgiving. Any other questions? Okay, I'll move to the PowerPoint now. And we'll have a little review at the beginning of this just to talk about various slides, the nature of the shapes, and kind of go over what we learned yesterday. And these slides are pretty good. So basically what I'm going to do today is essentially cover various aspects of this as well. So now I will share the screen with you folks, and please let me know that you can see it.
For the final, are we allowed a note card?
Yes. No, for the I don't know yet. I will know around the final time, but you will get that periodic table, all the formulas in the back. But I honestly don't know. Yes, you will be allowed a note card for the 4th test, but I don't know what's happening with the final yet. Any other questions? Okay, can you see the slides there? Can you see the slides okay on the screen? Can everybody see? Okay, very good. So let's start. The molecular shapes, how to do the structure. First, for example, if you want to know the structure of something, and I'll just start with here, like CH4. You start with CH4, like that. So basically you count the number of electron charge clouds there. So basically you write the Lewis dot structure first that looks like this. How many electron charge clouds are around it? Huh? 4, very good. You predict it, the geometry by it, assuming that their oriented space is far away from possible as possible. So what is the prediction for that one? Tetrahedral, okay? So we already addressed that in the last lecture on Monday, okay? So if we look at an example here with the CO2, for example, there are 2 charge clouds. And so this is linear with this one because, again, you got those electron pairs there, and this double bond is holding that in place. So that's a linear structure. Same thing with this other one with a bond angle of 180 degrees. So those are 2 possibilities there for that. And the charge cloud kind of goes up above and down below for each of these different structures. 3 charge clouds, it looks like this. So essentially you have a trigonal planar thing with 3 charge clouds. Okay, and there's a couple examples with that. 4 charge clouds, a tetrahedral thing, or it could be ammonia. Why is ammonia 4 charge cards?
Electron pair.
Yeah, very good, good. An electron pair, that is a cloud too, okay, just different. Now, what is the structure that it becomes if it's not tetrahedral? What is the structure that it becomes? Well, sort of, but it's sort of a pyramidal structure. But again, the only one I want you to know is tetrahedral, okay? So it's still tetrahedral, but it's kind of bent tetrahedral, okay? And then 4 charge clouds look like this, methane, and then ammonia, and the water molecule also, and that's definitely bent, okay? 5 charge clouds, a trigonal bipyramidal, and it looks like this. And again, you can see why I like these slides. They're better than the other ones. And it fits well with what we did last time. Okay, does anybody have any questions on these slides for this part? Those of you who are distant. Okay, and then we have the 5 charts there. And again, these are all trigonal bipyramidal, even though they might be variations of them, like a seesaw or the T-shaped or whatever else. So basically, the 5 charge things, that's trigonal bipyramidal. And then there's T-shaped and linear associated with that too. But again, they're still trigonal bipyramidal, irrespective of those other ones. And I'm not going to ask you to learn them. And then lastly, with 6, you have charge clouds around this. And right now, we don't particularly know how that happens, but that's what the next section is about. And it's about the use of these hybrid orbitals and how they form particular bonds that are particularly unique to each. And these are examples of the ones with 6. Okay, and the geometry around there, again, they have a nice table for it, and you can use whatever you want with it. Now, the valence bond theory is the next part regarding how these things are shared in a covalent bond. So here you have a 1s orbital comes close to another s orbital, and this now is considered what is called a sigma bond. And both of those orbitals are mixed together, and you've got the nucleus in the center of both. With fluorine, you have a 2p here. This merges with another one. So essentially this happens, and this is also called a sigma bond. So that's the other kind of bond that can happen when you have fluorine. Now, why does it look like that? What's the nature of the fluorine electron configuration? What is the nature of it? Well, you look on the periodic table, see where it is. You have a 2s2, 2p5. So essentially the 2s is already filled. Okay, and then you have the 3 p's like this, 1, 2, 3, up and down, 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 just there. And notice the empty spot there. Those two will merge together, and that's what the p comes close to the p, and then forming this also. That's also what is called a sigma bond. Okay, sometimes you have an s orbital, like for hydrogen, merging with a chlorine, and this is also called a sigma bond. And I like to represent it with this big thing and then a small one like that, but this is also called a sigma bond. And they're always present when you have bonding first. You always have a sigma bond with it.
Dr. Douglas,
Yes,
when you do that like 6 thing, is that a symbol for sigma?
yes, that's the Greek symbol for sigma.
Okay, thank you.
Chemists and physicists use the Greek alphabet commonly to indicate the different things. That's the Greek letter. Okay, and believe it or not, when I was in seminary, I took Greek and I said, oh, this is cool. I learned the Greek alphabet finally. But in any case, I always use it in the context of chemistry or physics.
And a sigma bond is just something that fills the p and s orbitals together covalently?
Yes, there's 3 kinds of sigma bonds. S plus S is a sigma bond because it essentially gives this, and then S plus P, and it gives this. This is S plus P, and then P plus P. And basically that's the previous slide, which is here. This is P plus P. P plus P gives this structure.
Why
That's
is that
sigma,
P plus
called a
P?
sigma bond.
Because those are the s orbitals.
Yeah, those are the s orbitals on that one. This is 1s1, right?
Yeah, so why is it? Oh, you're talking about the bottom one, I'm sorry.
Well, these are p orbitals mixing, because see, with fluorine, you have 2s2, and then 2p5. So basically, those are 2 p orbitals coming next to each other. You get the bond there. The s1 is already filled in both fluorines. So it's not involved in bonding. The ones that is the P one, but that's the one that sticks out the most anyway. Did that answer your question, Brandon?
Yeah.
Okay. Now, the next quantum mechanical model that shows how they are to with this. Essentially, these are all probabilities, and that's where quantum mechanics comes in. When I was in college as a senior and a junior, I took partial differential equations and differential equations in math, and I had a quantum chemistry class where we went into all the probabilities and everything, used the calculus methods and everything. I really liked it at the time, but over the years since then, because I never used it, I've forgotten most of it. But the thing is, the big picture here is what I want you to understand, the nature of these clouds, and they're essentially probability clouds, that it's more likely it's in the cloud area than not. Okay, particularly if it's a heavier cloud area. If you just look at clouds in the sky where you got a nice puffy white cloud, the center looks gray, the outer side looks white, well, same thing. They're all about, it's kind of like that. The more common it is, it would be in the middle of that structure. Covalent bonds are formed by the overlap of atomic orbitals, each of which contains one electron of opposite spin. So that's essentially what this box is referring to. When you have this, one goes up like that, the other one down like that. That's the opposite spin. So basically, if you have two ones that go up like this, and the other one from the other atom that goes down like that, this is hydrogen coming together. This is now the structure for the hydrogen here, essentially with the electron pair shared between them. They've essentially formed what is called a sigma bond. Okay, the greater the amount of overlap, the stronger the bond. So, how can this be explained? Well, basically, when you look at energy here, this is the electron configuration of carbon. This is the bottom layer. It's not involved in bonding. How many valence electrons does that have for carbon? No, valence electrons. 4. Okay, and how can it form 4 bonds? Well, one of these will shift up here, and then essentially they all average out. So you get now 4 possible bonds, them all going up like this, according to what is called Hund's rule. So you now have the 3-dimensional structure of what is called tetrahedral of those around it. And that's why we put carbon as being 4 dots all separated, not carbon like this. Okay, you don't put it like that, even though practically that's what it is. You separate them all out because this is how they form bonds. Does everybody see what I'm doing with this? This goes up in energy, these go down in energy, equivalent amount. Okay, so the thing is now these are all equal energy as you go across. So essentially you've got a shift of the electron up to where it's at a higher, to whether it's at a more stable position along with the other electrons, they move down a little bit. So the overall average is the same, even though things. And again, electrons are interchangeable. So essentially they want to all balance out and get as far apart from one another as possible.
Can you re-explain that? I didn't really understand.
Okay, well here, this is another good example. What's happened to the electrons on the 2 electrons? What happened to the other one? Where'd it go, Brandon?
It went up to the P.
Correct. And in a way, I don't like this box the way they do on the slides, because it's more appropriate done with 4 like this, all at the same level, because this one has gone down, this one has gone up in energy for the overall there, because all the different shapes that go out in the 3 directions, these are all p orbitals, okay? And they were all equal around, they're all equal in energy. And so basically you have the p orbitals there with the s down below. And so now these all shift and you can have the 4 different directions with the tetrahedral structure. So essentially you have 4 non-equivalent orbitals shifts to form this. This is called hybridization, and it is Sp3 hybridization when you have 4 like this. Essentially this level goes down. You see where this is the level of it. These 3 move down. These move down. This one moves up for the equivalent be here. So now you have sp3 and you have 4 of those orbitals. That's what's called a hybrid orbital, 4 equivalent orbitals that form in that tetrahedron, in the tetrahedral shape. Okay, now this is how they show up. These are the shapes now. You see, this is the orbital shape, right, for the S. This is the orbital for the S. What does the shape of the other ones? Brandon, I'm going to ask you here. What's the shape of the other ones next to the, below the S there?
What do you, those are, what do you mean?
These here, what's the shape of those? That's like a dumbbell, right?
Yeah, so it's a p orbital.
Yeah, so basically the S orbital kind of merges with the P plus the P like this, and you get a lobe that looks like that. That's called an sp3 orbital, and there are 4 different arrangements in 4 different directions there. And if you were to do a dipole moment, they would all cancel out. Whether it's the arrows go that way or in towards the center, which because carbon's more electronegative than the other one. So basically these 4 lobes orient around that tetrahedron, okay? So that's essentially the hybridization that occurs with these. Okay, so that's the structure you now have. The 4 hybrid orbitals, and that's why I represent this. You put the carbon with 4 around it. That's why at the very beginning, 2 weeks ago, I gave you the periodic table and used the X with 1 dot and then going around to 7, and I spread them out on purpose because it was predicting moving forward to this. Now you know why, because it forms these hybrids. Unfortunately, there are books that put carbon to be its electron configuration to look like that. I hate them with a passion because it's confusing. That is not how they form bonds. That will mislead somebody if they do it. That's one reason I like the graphical approach and not counting them up like the book recommends, to count them all and then put them all around, because you miss this whole geometric aspect of being able to picture it in space in front of you. I learn visually in this way, so I find this graphics very cool, and I hope many of you can appreciate that as well. I can't see the expressions on your face, virtual people. Does everybody understand this slide here, how this kind of works?
I get how the S and P come together, but I don't get why it's hybrid to start out with, why the carbon is hybrid to start out with.
Yeah, that's because of this thing. Essentially, so it can it can go to 4. Here, how many bonding electrons are available for them with this structure for carbon? How many bonding electrons are there?
6.
No, the ones that are available to pair with another one.
2.
Just 2, okay? But that's not how carbon's going to act, because they all go around the carbon and they'll want to equalize. So the result is it goes to 4 like this, like that. And hopefully that answers your question, because what is called a hybrid forms. And I will explain that a little bit when we talk about pi bonds, because pi bonds involve full p orbitals. They are not involved in other kinds of hybrids, and that is involved in double and triple bonds, in involving those pure p orbitals merging together, and I'll get to that in a minute. Okay, so the sp3 hybrid like this. There are other kinds of hybrids too with an sp2 orbital, and basically the way that works is, say you have boron trihydride, okay, boron hydride, and basically boron, how many does that have around it? In its outer shell, how many does that have around it? 3, okay? So essentially you have now the 2s2, one like that, and then the p's are empty except for one of them. What is the hybrid that will form? This is now sp. What is the hybrid that will form when one of those shifts? What's going to happen to it? It will go to form, it'll move this one to here, this equivalent, and now you have what is called Sp2 hybridization. And that's what this is down below, where you have an Sp2, and it's related to a boron here, and essentially boron is in the center with an Sp2 hybridization, and it could be either empty at the top and the bottom, or it could be an electron pair at the top and the bottom. But basically, or a double bond in those kind of settings, and we'll explain that in a minute. Okay.
Dr. Douglas,
Yes.
like, I don't understand. So, like, the boron would, the last three, the p orbital would become full. Like, there'd be three.
Yes, because you'll have one going up like that, one like that, and then this one will be empty and not be involved. That's the empty space at the top and below the boron. So
But why is
boron,
there a fourth
the
one?
boron structure will look like this. It's trigonal planar with no electron pair at the top and the bottom.
But why is there a fourth one?
It's just empty. It's just that these are the 3 p orbitals. Okay.
I understand that, but you had 4 blanks. Why? Where did the fourth one come from?
Well, that's them forming hybrids, but there's only 3 electrons available, so it forms what's called Sp2. The Sp2 looks like this. One there, one there, one there. 3 bonds, and then the last. This is the S that started as S2, but it's now S1. You have a P1, P2 now, and this one is empty. Okay. And that's the empty spot here above and below. There's nothing that can be there.
So it has 3 electrons in the hybrid orbital, right?
Yeah, that's called Sp2. And if you have Sp2 that looks like this, S1, P2, what's the total of 1 plus 2?
3.
3, yes, 3 bonds possible, 3 sigma bonds possible.
Dr. Douglas,
Yeah,
so would you say that when taking the terms of what we've been talking about with the hybrid orbitals,
yeah.
does it not only, would it not only work for elements in group 13 and group 14A?
And 15 and 16, and I'll show you in that in a minute.
Okay.
Okay, and even 17, because 17, which includes fluorine, chlorine, whatever, they just have a sigma bond with a neighbor, just like I showed you here with HF. HF, because fluorine has 7, like this, and it has, this is the S orbital, this is the 1p that looks like this. That's on the earlier slide coming in like that. That forms a sigma bond also, okay? So that becomes a hybrid there with an Sp hybrid. Sp hybrid. Okay, so basically there's another kind of bond here. This is a double bond, and where this comes from is if you take a p orbital, there's 2 p orbitals. If you combine 2 p orbitals that look like this, and based on what we did before with the merging, okay, we have another p orbital that looks like this, right? What happened with this p orbital? What happened when you merged those together? What did you get on the other side? Well, you get something like this, with a big lobe there and a little one there. This is a sigma bond also, okay? So you have this p plus this p coming in together. This merges in the middle, and an example of that would be fluorine. Okay, F2. And you could draw that for yourself with the fluorine. Essentially, fluorine is 7, and as that, the other fluorine is the 7 here. That forms a bond right there. This is this kind of bond. It looks like this. Now, forming a double bond, okay, this essentially involves these kind of things, because this has to be pure P. They are not hybrids, really. They are pure P's. 2 pure P's give this kind of bond here. So the result is you get a lobe on top and one below. And that's what would keep things flat. Okay? And then also you have another one that one S and one P will give two Sp hybrids there, where you have one S and one P orbital attached available, and you'll get an Sp hybrid. And that example is essentially where you have a hydrogen that's an S here, and then the fluorine, which has a P. And this is the nature of that thing. And so that is considered linear. Okay. And then with this one, the other kind of thing, if you have this p orbital here and this p orbital there, they merge. So basically you could have a p orbital like this plus a p orbital like this. They merge to form this structure. You can also have a p orbital that looks like this with out in front, plus another one going back behind and out in front, and that gives a thing back behind and then one in the front, and that's what this is referring to. So basically there are two kinds of pi, and these are called pi bonds. Pi bonds. Now, that's the Greek letter too, pi, but what letter does that give you? The P. So pi bonds happen when you have two p orbitals merging together. Okay, and basically I will go through some examples of that on the next slides. Yeah, or side to side, and they'll form those kind of things because the clouds merge. And again, it's probabilities. It's like this cloud comes close to this cloud. Remember, there's one electron in each orbit, right? So they can go up above and below, and that's what keeps it flat. Okay. Now I'm gonna end the slideshow for a minute and add a slide to it so I could show you an example. I'm going to add a slide here. Just a minute. I'm going to add a slide to it. Okay, so I'm going to put two slides in with this now, and then we'll go back to the sharing of the screen. Okay, can everybody see the blank now? Okay, now, what kind of structures would be formed by these? Well, let's look at two possibilities. And basically, I'm going to fix the pen so it goes like this. C2H4. Okay, what's the Lewis dot structure for this? Well, you put the carbon next to the other carbon, 1, 2, 3, 4, like that. This carbon comes in here like this. Okay, this forms a bond. How many spaces are left? 6. That's a problem because you only have 4 hydrogens. So you put the 4 hydrogens in here like that. And remember, this is a p orbital sticking out. Here, this also has a hydrogen, and this is a p orbital sticking out. So essentially what happens with this one is essentially now these two will merge together and you get what is called a double bond, and it looks like that. Okay, so basically this now has one sigma bond that comes from the two p's that come close to each other like this to form the single bond between those two, and then the other pi bond that happens with this plus this, and essentially you get the double bond, and essentially now this is trigonal planar, and believe it or not, this is part why it is considered planar or kept flat, because you've got this lobe above and below it holding it in place. It's kind of like you've got a rubber band on the top and the bottom, so basically it will not twist and it will remain flat. So these hydrogens are as far apart from one another as possible. That's why a double bond is stronger than a single.
And is that the pi bond?
Yes, correct. Yes. Because essentially what has happened with the carbon is the carbon. Remember, we had a structure that looked like this, 2s2, 2p2, right? We had 2s2, 2p2 for carbon, four there. Well, one of these p's is required. So now you have one of these p's is required. So essentially you take one of them away and shift it. So basically the hybrid becomes Sp3. So you now have four like this. This is the Sp3 structure, but it needs one p orbital there to form this kind of bond, the double bond in that. So now this becomes, because this is pure p, this now becomes Sp2, and that is called an Sp2 hybrid. Because this one is gone, it's a pure p, it did not form a hybrid orbital. It's a pure p, and that's what this sigma bond is. Okay, now,
In that hybrid orbital, where do the electrons go? Can you draw them out on the lines?
well, yeah, let me erase some of the slide. Okay, remember with carbon, it looks like this. Remember with carbon, it looks like this. Carbon is essentially 2s2, 2p1, 2p2. So essentially it looks like this with the boxes. You have the 2s2 like that, and then the 2p2 like this. Up like that, there. Okay, so that's the structure. What happens to that to shift it? To Sp3. Yes, one moves up here, so now this could be Sp3. However, if this one is needed for a pure P, okay, to form the double bond, this one will look like this and merge with another one to form the bond above and below like that. So that is required, the pure P, so it is no longer Sp3 hybrid, it is now Sp2 hybrid. And all trigonal planar forms are the Sp2 hybrid, just like the other ones. So essentially, hopefully that answers your question, but the reading in the book will help you even more. Okay, now the next slide is another example, C2H2. Okay, what is that electron configuration for the carbon going to be? Well, you start off with the 2s2 like up like that, up like down like that, and then you have 3 p orbitals like this, one up like that, one like that. Okay, you have 2 p orbitals available. One of these shifts here, but you only have 2 hydrogens available. So these essentially look like this, come next to the other one. You put a hydrogen over here, that forms a bond. This one forms a bond on the other side. But now you've got 3 bonds now. This is the PP. This is in the middle. This is the one with the 2 P's there. Go like this in the middle there. And then this is a sigma bond. And this is the S and the P there, S and the P there. But here you now have a bond here, above and below, and also behind and in front. So essentially you can have a triple bond here with this that forms that, and that is called an Sp hybrid, which are all linear. And that's what the earlier slide showed you. And it's the same thing if you have HCN that looks like this, because these pi bonds require the p orbitals. The pi bonds require the p orbitals, require pure p orbitals. They can't be hybrid in the other ones, orbitals. Okay?
Dr. Douglas?
Well, it's just there's no hybrid forming. It's just the hybrid is the two coming together with just merging. They don't have the fancy look like the big one. Okay? Yeah, they merge together and they form the lobe above and below like that. That's it. and essentially they'll come in next to each other, and it'll be like, it'll be combined, like the carbon will be like this. You have the P's shaped like this, and you'll have up and down there, and then another one up and down there, and then another one there, up and down, but these are pure P there, and you have the SP there. So these are the ones that are pure P for the double bond here, and the other one for 3 of them around it. Yes. Someone had a question, Nick?
Douglas.
Yes,
So C2H4 had 1 sigma bond.
correct, then 1 pi bond.
So this doesn't have any sigma bonds, or does it have 2 sigma bonds? C2H2.
C2H2, it has 1 sigma and 2 pi's.
Okay.
Okay, and if you put the 3 like this, there's always a sigma. The sigma is here. The 2 pi's are this one and that one, because they form like this. There's 2 of them, 3-dimensionally, like this slide, Nick.
Okay, I see.
Okay, and the other one's just twisted a little bit, 90 degrees into the plane of the board. Now, hybrids with these 2, the hybridization that happens with a linear, these are Sp hybridization, and this example I showed you before looks like this, okay? The trigonal planar Sp2, that looks like this. Or it could look like this. Why does it look like that for this one? Why this? Why is that Sp2? You have 1 double bond. You have 1 sigma and 1 pi. Okay? And basically they fit very well in there. Okay? Now, polar covalent bonds and dipole moments, we already addressed that earlier in the other slides. Yes. And then polar covalent, we already addressed this regarding these slides. Intermolecular forces, that's the next thing talked about. And I'm not going to address these in the class. That comes for solutions. And so essentially we are done with these slides, and I'll go back to the other slides to finish off the chapter. Next thing. So the intermolecular forces part is not included for this next exam. It's better covered in solids and liquids, okay? But it's not included in the next exam. So this is a good endpoint. Any questions? Yes. And hopefully you could visually see it too there. Now, why is this linear? What is the hybridization for this one? There's 2 sigma bonds and then 2 pi bonds. So why is that? What is that hybridization? That's Sp also. Yeah, very good. Because one double bond is holding it one thing, the other double bond's holding it the other way. You got one double bond like this, the other one like that, and they kind of switch. So it's like a hot dog bun around the whole thing.
So there can be more than one type of bond in a bond.
Yeah, sigma 1 and then up to 2 pi bonds. And when you get into the trigonal bipyramidal and the octahedral structures, those are all sigma bonds, but they're all split. There's no double bonds with those structures because they're all sigmas. Like, for example, if you have XF6, that's an octahedral structure, and so that'll be xenon, that'll essentially be uranium F6, that's another one. Those essentially either be ionic or they'll be octahedral, and they're all sigma bonds there where they're shared just as a sigma form. Any other questions? Okay, we're done for the day. I'll see you folks tomorrow at 9 o'clock.